3 days ago, the atmospheric index that measures the strength of the Antarctic polar vortex climbed to plus 5.0. That number is not a routine weather statistic. It is one of the highest values recorded in the modern observational era, and it is sitting there right now, spinning at the bottom of the planet, building cold pressure against the southern edge of the most important coffee-growing region on Earth. The forecast keeps it elevated at plus 2.0 or higher through the first third of July. Before this video is over, you are going to understand exactly why the number is the most important figure in global agriculture right now, and why the word rare in the title of this video is not an exaggeration. It is a precise meteorological classification with a specific historical record attached to it. A record that every coffee grower in Brazil, every commodity trader watching futures, and every coffee drinker wondering why their grocery bill keeps climbing should be paying very close attention to right now. Let me start with what is actually happening in the atmosphere, because the mechanism is the part of this story not getting the attention it deserves outside of specialist forecasting circles. The Antarctic polar vortex is a massive, continent-spanning circulation of intensely cold air sitting over Antarctica, locked in place by powerful westerly winds running around the outside of the continent. In a normal winter, this system has a natural breathing cycle. It strengthens, it relaxes, it shifts position slightly, and the cold air it contains either stays locked over the pole or finds pathways to leak northward into the mid-latitudes of the southern hemisphere. The Antarctic Oscillation Index, the number that tells us how tightly wound and organized that circulation is, typically runs between minus 3.0 and plus 3.0 across a normal seasonal range. Plus 5.0 is not a normal reading. It is an extreme reading, and it is where we are right now. What makes this specific reading particularly significant is not just the intensity of the vortex, it is the position. The current polar vortex center is displaced toward the Amundsen Sea sector of West Antarctica. Climate scientists and long-range forecasters have identified the Amundsen Sea positioning as the specific vortex configuration most historically associated with a downstream atmospheric wave pattern that sends cold air northward into South America. When the vortex center sits over the Amundsen Sea, it acts like a stone dropped into water. The ripples propagate northward and eastward through the mid-latitude atmosphere as alternating ridges and troughs in the upper-level flow. The trough that develops downstream off the eastern coast of South America is the mechanism that disrupts the subtropical high pressure normally blocking cold polar air from penetrating into Brazil's interior. Climate Impact Company described this configuration directly. The polar vortex location near the Amundsen Sea historically produces a dipole trough off the central east coast of South America during winter, causing a cold pattern for Argentina and creating a cold air source region capable of surging into Brazil and threatening coffee growing areas. That is the setup present right now. The question is not whether the setup exists. It clearly does. The question is whether the specific wave deepening required to open the corridor northward will materialize before the vortex relaxes back toward neutral. To understand why that question matters so much, you need to understand the difference between the kind of frost Brazil's coffee belt experiences most winters and the kind that changes the global coffee market for years. And this is where the word rare becomes a technical term rather than a dramatic one. The frosts that moved through southern Brazil around the winter solstice on June 21st and 22nd were primarily radiational frost events. A cold front pushes through a region, high pressure builds behind it. Skies clear, winds go calm, and overnight the ground and vegetation radiate their stored heat into a clear, dry atmosphere, and surface temperatures drop hard at the local level. Those events cause genuine crop damage. Reports out of the Cerrado Mineiro region, southern Minas Gerais, and parts of São Paulo state confirm the June wave caused measurable damage in the southern and higher altitude portions of the coffee belt. But a radiational frost is fundamentally a local surface phenomenon. The air mass does not need to be genuinely polar. It simply needs to be cold enough, dry enough, and still enough for the surface cooling physics to do the damage. Brazil's winter, even in a below-average frost year, can produce those conditions with some regularity. What is categorically different, what is rare, is a true polar air outbreak. A frost event that does not form locally under calm skies, but instead arrives because Antarctic air has physically traveled thousands of kilometers northward from genuinely polar source regions, across subtropical South America, penetrating into latitudes that normally sit well within the tropical air mass domain. For that to happen, the cold air needs a sustained atmospheric corridor, a pathway that breaks through the subtropical high-pressure ridge that otherwise acts as a permanent cap on polar incursions at those latitudes. The only thing that reliably opens that corridor is a polar vortex displacement into the Amundsen Sea sector, producing that downstream trough off South America's east coast, pushing the subtropical ridge northward and allowing cold to surge through the gap. Without that gate, you get June-style radiational frosts. With it, you can get something the Brazilian agricultural community has a specific and very serious name for. You can get a black frost. The difference between a white frost and a black frost tells you everything about why the worst moments in Brazilian coffee history are specifically July events. A white frost is what most people picture. Ice crystals form on exposed surfaces. Temperatures dropped, moisture condensed and froze onto leaves and soil. The ice is visible, the damage is visible. And because ice formation on a surface releases a small amount of latent heat through the same physics that makes protective overhead irrigation work, a white frost has a partial self-limiting quality. The plant is cold. But the surface ice provides a thin buffer against the absolute floor temperature. A black frost forms under completely different and far more extreme conditions. Temperatures drop well below freezing to -4, -5, -7 degrees Celsius, and the air mass is so dry that there is essentially no available moisture to condense onto surfaces. Ice does not form on the exterior of the plant. Instead, the water inside the plant's own cells freezes directly. There is no external warning sign. The plant looks completely normal at sunrise. And then, as morning temperatures begin to rise, the cellular damage expresses itself catastrophically. Leaves blacken and collapse. Woody stems crack from internal ice expansion. Entire fields that appeared intact at dawn look within hours like they have been swept by a wildfire. The Brazilian coffee. Industry calls this the burnt appearance, and the description is accurate because the visual result of an extreme black frost and an actual fire are genuinely difficult to distinguish from a distance. On July 18, 1975, a black frost swept through Paraná state in southern Brazil. Paraná was at that time one of the largest Arabica coffee-producing states in the country. Temperatures in some coffee zones dropped to -7 degrees Celsius. The polar air outbreak was deep enough to reach latitudes that, under normal conditions, are shielded by subtropical air mass dominance. The frost did not just damage the crop, it effectively eradicated coffee production in Paraná. Millions of trees were killed outright, not damaged, not stressed. Killed, requiring complete replanting across enormous areas. The destruction was so total that Brazilian coffee geography was permanently altered. Today, Paraná produces essentially no Arabica coffee at all. The industry migrated north and west to regions like the Cerrado and southern Minas Gerais, seeking higher altitudes and, by moving northward, reducing exposure to the exact kind of polar air outbreak that 1975 demonstrated was possible. Within 12 months of the July 1975 Black Frost, world Arabica coffee prices had roughly doubled. The supply shock ran for years, not months, and the scars on the Brazilian coffee landscape were measured in decades. The 2021 frost season produced a second critical case study. The first frost in southern Minas hit around July 1st, described as serious but geographically limited. Growers in more northerly parts of the coffee belt found limited visible damage and began to feel the worst had passed. 20 days later, on July 21st, a second cold wave hit. This one reached the Cerrado Mineiro and the Alta Mogiana region of São Paulo state, areas that had survived the July 1st event largely intact. The damage from the second wave was dramatically more severe than the first, even though absolute minimum temperatures in some locations were not dramatically lower. The reason is a process called cold hardening failure, and it is the mechanism that makes a second frost in a sequence categorically more dangerous than the first at the same temperature. When a coffee tree experiences its first cold stress of the season, it triggers a metabolic response. The tree increases production of soluble sugars, specific protective proteins, and other cryoprotectant compounds that lower the effective freezing point of the water inside its cells. This is the tree's biological version of antifreeze. It takes time to build, and it depletes under sustained cold exposure. A tree that has been through one cold wave and is still in recovery has not fully restored its cryoprotectant levels. That tree is physiologically more vulnerable to a second wave than it was to the first, even at identical temperatures. In Brazil's coffee belt right now, the trees are already in exactly that position. The June 21st and 22nd event pushed lows to near 2 degrees Celsius in the Cerrado Mineiro, with frost confirmed across parts of the region. The trees that survived did so with their cellular defenses engaged. They are now sitting in cold, dry, late June conditions, still stressed, still not fully recovered. If a second outbreak reaches those trees in mid-July, when the polar vortex is at historically extreme intensity and the cold air reservoir south of Brazil is at its deepest of the winter, those trees will face the second event with measurably less biological capacity to resist it. This is precisely what happened in 2021. The second wave hit harder because of what the first wave had already taken from the trees. The The coffee market's current pricing reflects none of this specific risk. Arabica futures are trading around 260 cents per pound, bouncing from a multi-year low, near 250 earlier this month. That bounce was driven by June 21st cold wave headlines, but the market is still pricing a scenario where the frost season produces limited damage and the remaining winter months pass without catastrophic revision to the current supply narrative. What the market is not pricing is a second, more severe wave in mid-July, finding a tree population already cold-stressed and physiologically compromised. The physical supply backstop that would normally cushion a price reaction is also essentially absent. ICE-certified Arabica stocks sit at roughly 396,000 bags, against 859,000 bags held a year earlier, less than half. Multiple analysts have noted the difference between confirmed damage in primary producing regions, and a clean pass without crop impact is the difference between a breakout toward 320 cents and a retest of 240. We are at the exact inflection point where the next atmospheric decision over Antarctica carries direct price implications for every cup of coffee purchased anywhere in the world. I want to be direct about what the current forecast actually says. The 15-day model guidance has the cold staying south of the atmospheric preconditions for an extraordinary event are present right now in a way that does not occur every year. The Antarctic oscillation at plus 5.0, the polar vortex centered near the Amundsen Sea in precisely the configuration climate scientists have identified as the historical precursor to East Coast South America dipole troughs. A 15-day forecast keeping the cold just south of the coffee belt inside genuine model uncertainty. A tree population already cold stressed from the June event. A market priced for recovery with no physical supply buffer. The window I am watching most closely runs from approximately July the 10th through July 25th. That is the period when the midwinter pattern typically produces the deepest polar air outbreaks into subtropical South America. It is the period that produced the July 18th, 1975 black frost and the July 21st, 2021 second wave. Every day the polar vortex holds its current extreme intensity. The cold reservoir available for a potential surge grows deeper and the probability of a mid-July breakthrough increases. The difference between tracking this and this is happening now, and a pattern like this one can be a matter of 48 hours. I will be monitoring medium range models every day through July 25th. If the forecast shifts in a way that puts cold air penetrating north of its current boundary, I will be back immediately. The polar vortex spinning at plus 5.0 over the Amundsen Sea right now is not finished making its argument. Subscribe and turn on notifications. This one is time sensitive in a way that genuinely matters.